Hello, so this is section 5.1 video 3, and I actually just got done recording video 2, and I was so excited about this video that I just decided to do it right away. We're going to look at these 4 examples on the worksheet. I'll say them on the board before doing each one. These are some of the problems that I just really love about math, because they're just these kind of like fun little puzzles that you get to work through. And so, but they'll also show us some really, really important sort of foundational concepts that we can start sort of applying with eigenvalues. So for example, number 1 is almost just an extension we'll see of a very well-known theorem in this course, or a very big theorem in this course, I guess I should say. I think then a few of these will give us sort of insight onto how to sort of construct counterexamples when we're looking at these true or false questions, and maybe what to look for in some of these more theoretical questions. So we'll jump right in. All right, so I want to show that if 0 is an eigenvalue of A, then A is not invertible. Okay, so let's suppose that 0 is an eigenvalue of A. So notice that implies that this matrix equation has a non-trivial solution. What is this matrix equation? Well, so certainly this means, right, so this is if 0 is an eigenvalue of A, then we get that, right? Because this is just by definition, if something is an eigenvalue, it satisfies this equation, or this equation has a non-trivial solution. Well, 0 times I is just a 0 matrix, right? So this here just implies that A times x equals 0 has the same non-trivial solution. Well, and now we can just call on the invertible matrix theorem, which I will refer to as inv-mat fm. A is not invertible. And in fact, I didn't write this on the board, but this is actually an if and only if, right? That if A is not invertible, then also 0 is an eigenvalue of A. Because, remember, if A is not invertible, then this has a non-trivial solution, which means this has a non-trivial solution, which means 0 is an eigenvalue of A. So kind of cool. We now have yet another way of determining if a matrix is invertible or not by checking its eigenvalues. If it has a 0 eigenvalue, not invertible. No 0 eigenvalues, not invertible. So 1 is actually a very important fact that I definitely wanted to get in there because it's, well, like I said, very important. All right, so number 2. We want to construct an example of a 2x2 matrix with exactly 1 eigenvalue. So this will come in handy. So this type of a thing, the ability to kind of construct these matrices with desired properties, is very useful sort of in these true or false questions, right? Because often we're given this statement, like we have to prove or disprove this thing, right? And the way we disprove something is by finding a counterexample. So it's good to sort of have some of these tools of like, okay, I want to construct a matrix with, this property. What's the easiest way to do it? So it turns out, again, if we're trying to control the eigenvalues of a matrix, the best thing we can do, and we don't have any other restrictions on that matrix, right? Well, the best thing we can do is use theorem 1 from last video what does theorem 1 tell us? Well, that all of the eigenvalues of an upper or lower triangular matrix fall on its diagonal. So if I want an example of a 2 by 2 matrix with exactly one eigenvalue, I might just construct a matrix that is upper triangular and has the same repeated diagonal entry. So notice this is a 2 by 2 matrix with exactly one eigenvalue. And so notice, like, if you were maybe asked to construct a 3 by 3 matrix with eigenvalues 1, 2, and 3, you would just construct an upper or lower triangular matrix. You would have to make sure that its diagonal contained the entries 1, 2, and 3. But then after that, you'd be free to put any entries you wanted to in the upper triangular part of the matrix, right? And so certainly this theorem 1 here, where we can kind of control the eigenvalues of a matrix if it is upper or lower triangular, is extremely useful. All right, so that is 1, 2. So if you'll remember with determinants, let me make sure I'm doing the correct one. Yes, okay. So if you remember with determinants, we had this nice relationship between the determinant of A and its inverse. It turns out that with eigenvalues, we also have a nice relationship between the eigenvalues of A and its inverse. That is, if lambda is an eigenvalue of A and A is invertible, right? And so now we know that this means that A has no zero eigenvalues. Well, that means that 1 over lambda is an eigenvalue of A inverse. Well, why is that? So if I were to try and sort of approach this problem of trying to show this, right? So let's say, I didn't know that this was true. The first thing I would do is look at a 2 by 2 matrix, right? And quickly check, just find a 2 by 2 matrix that was invertible, look at the eigenvalues of its inverse and say, okay, is this actually a thing that's going on? And like I said, generally with these problems, if you kind of check a few 2 by 2 and 3 by 3 matrices and you don't find any sort of counterexample, generally that's an indication that you should try to start convincing yourself that this statement is always true, right? And so here, we're sort of starting out by knowing it's always true. So then how do we prove this statement? Well, so whenever we want to prove this, we want to start with something we know. So I always like to write down something we know. What we know is that A times X is equal to lambda times X, where X is a non-zero vector, lambda is the eigenvalue, and A, of course, is this matrix. Then I like to think, okay, where do I want to end? Well, I want to end by showing that A inverse times some vector y is equal to 1 over lambda times y, right? So I don't know anything about the vector y, so that should give me a hint that maybe I already know what y is, right? If I'm not really given y, I probably have to find y in the material that I already have, right? So like I want to somehow get here from here. Well, what's one tool I have? I can multiply both sides by A inverse. So on the right side of this equation, or on the left side of this equation, excuse me, I'm left with X. on the right side, I can factor out lambda and get that x is equal to A inverse times x times lambda. Well, and now I just divide by lambda on both sides. And so notice here that I don't have to worry about lambda being 0 because of problem 1 in this set, and the fact that A is invertible means that lambda can't be 0. And so it turns out that this eigenvector is actually the same eigenvector here as it is here. So that is, if lambda is an invertible matrix, or lambda is an eigenvalue of an invertible matrix A with eigenvalue lambda, then 1 over lambda is an eigenvalue of A inverse corresponding to the exact same eigenvector. If that's not cool, I don't know what isn't. So, one more problem. So now we want to show that if lambda is an eigenvalue of A, then lambda squared is an eigenvalue of the matrix A squared. And so this this actually proof will be very, very similar to number 3. So if you haven't looked at number 4 yet, I would actually highly encourage you to pause the video and actually try number 4 basically in a very similar way that I did number 3, with just sort of a slight change in that, you know, we're not looking at A inverse this time, we're looking at A squared. But otherwise the proof will be very similar. So yeah, pause here and try it. All right, so we're going to actually start out the same way, right? So we're assuming that here lambda is an eigenvalue of A, and so if that's the case, then I've got this corresponding eigenvector x. And again, where do I want to wind up? Well, I'd like to wind up by showing that for some vector y, that lambda squared is an eigenvector of A squared, right? So this is what I want to show. This is what I know. Well, much like before, since I've already started out with an A, maybe I'll just multiply both sides of this equation by A squared. And again, I can factor out a lambda, right? Well, I know that A times x, as I've already assumed, so this time I'm going to use this A times x that I've got by multiplying both sides times A. Well, that's equal to lambda times x, and so I get that A squared times x is equal to lambda squared times x. So notice in particular too then that 4 could apply to any power of A and any vector x, right? That if lambda is an eigenvalue of A, or sorry, any matrix A and any eigenvalue lambda, that if lambda is an eigenvalue of A, then lambda to the n is an eigenvalue of A to the n for any integer n. So that wraps up section 5.1. And so next week we will start section 5.2. Well, so yeah, going by the schedule, next week we will start section 5.2.